We've already looked at a central angle. A central angle has to have its vertex at the center of the circle. An inscribed angle is an angle formed by two chords with a vertex on the circle. An inscribed angle, so Branson, is this an inscribed angle?
No.
No, why not?
Because it's not going through the hole.
Does not. I didn't ask central angle. You're right about central angle. AOB then, since O is a center, is a central angle, right?
But A, nothing.
Okay. No, it's not. Okay. Now let me say again what the word inscribed means. Listen this time. It is an angle that formed by two chords whose vertex is on the circle. So, is this then an inscribed angle?
Yes.
Why not? Because the vertex is not on the circle. So, Branson,
That
is this an inscribed angle? Because it's connected to where? Because this point right here is called the vertex of the angle, and it is on the circle. Okay? So angle APB is an inscribed angle.
Ow.
Okay, here's another one that I want to ask you. Is it an inscribed angle? So are you ready, Branson? Okay. Is angle AQO an inscribed angle?
No.
So there's one more thing that has to be true in order for it to be an inscribed angle. Yes, the two sides of the angle have to be chords, Branson and Dustin. I'm trying to teach you specifically because you're not paying attention.
It says that is one.
Okay. The reason why it's not an inscribed angle is because the two sides have to be chords. QA is a chord, but is QO a chord?
No.
No. A chord has to have its endpoints on the circle. Now is this angle, AQC, an inscribed angle?
Yes, yeah.
Yes, it is. It doesn't matter if one of its chords goes through the center. As long as this diameter is a chord, by the way, okay? As long as it's formed by two segments that are chords of the circle, and its vertex is on the circle, then it is an inscribed angle. Okay, so an inscribed angle, let's write this definition up here, is an angle whose sides are chords and whose vertex lies on the circle. So my examples here, angle APB is an inscribed angle, and angle AQC is an inscribed angle. Alright. Now, Theorem 9.7 deals with inscribed angles. Theorem 9.7 requires 3 cases to prove it. Because when you draw an inscribed angle, you can either have one of the chords be a diameter, like I have it here, or you can have both chords forming the angle so the center is not in the angle, or you can have the chords forming an angle so the center is in the angle. Hannah? Inscribed angle? I don't have an abbreviation. If you want to make up one for your notes, you could. So Theorem 9.7 says the measure of an inscribed angle is equal to half the measure of the intercepted arc. When we do the proof, you'll see that it's related to the exterior angle of the triangle. Kind of like that problem number 10 with the box we filled out. So, Theorem 9.7, I have 3 diagrams to draw. The first diagram is where the inscribed angle actually has one of the sides as a diameter. Okay. The second diagram that we're going to draw is that the center is on the inside of the inscribed angle. The third diagram we're going to look at is the center is not inside the inscribed angle.
Are we all part of that?
They are. There's 3 cases. In all 3 cases, the way we're going to label this is we're going to call these points A and B, this point C. And in all 3 cases, our given is going to be the diagram. And what we want to prove is that that inscribed angle is half of the arc AB. So we'll write the given and prove here in this spot. Our given information is the diagram. And what we want to prove is that measure of angle ACB is 1/2 the measure of arc AB. Yeah, I want you guys.
Some people know. Not my right. It is not the economics.
We're going to prove that angle ACB is 1/2 the measure of arc AB. In all 3 cases, we're going to have exterior angles of a triangle. In this one, I draw from O to A, and we're going to be talking about angle 1 in comparison to these two angles. Why do I know these two angles are congruent? Isosceles triangle because the radii are congruent, right? So here, I'm actually going to draw 3 radii, so to speak. I have a diameter and then these radii. So I know that all of these segments are congruent. I'm going to be talking about angle 1 and angle 2 in comparison with these angles for angle 1 and these angles for angle 2. On this third diagram, it is the hardest to picture because we have to actually subtract angles to think about it. If I draw the diameter from C through O, then my two triangles are O to A, and we're going to talk about, well, let me draw my other triangle first, also from O to B. We're going to talk about then, okay, new scene right. Branson, you're over there on that side of Hannah. Okay, Dustin, you are back there beside Jessica. Move your desk beside her table.
I can't see that.
That's not my fault.
Yeah, it is.
Do you really need to sit closer?
Yeah.
Okay. I can put you right here. All right. Now here again, we're going to be working with the angles of these two triangles. I think you're kind of in Mark's viewpoint. So you want to sit right here, or we'll get you in a spot where we can do this. How are you guys? You're good? Okay. I want you looking up here anyway, so we're good. Okay. So I need this point in this diagram. We're going to call this point D, and we're going to be working with angle AOD compared to these angles and we're going to be working with angle BOD, which we'll call angle 2, compared to these angles. 3 arcs there. So angle 2 is angle BOD. It's just that piece. Okay. So on this one it's harder because we have to work with subtraction of angles, but we can get there. All right. So working with these diagrams, I'm going to move them up just a little bit so I can still keep track of that stuff and write notes. What I know is by Theorem 312, can someone look up Theorem 312 and then read it to us? So by Theorem 312, the measure of an exterior angle in a triangle, angle 1 is an exterior angle, is equal to the sum of the two remote interior angles. So I know then, by theorem 312, that the measure of angle 1 is equal to the measure of angle C plus the measure of angle A. And since C and A have the same measure, by substitution, I could say then that the measure of angle 1 is 2 times the measure of angle C. Which means that angle C will be half the measure of angle 1. The measure of angle 1 is how we get the measure of arc AB. The measure of the arc is equal to the measure of the central angle. So I can say that 1/2 the measure of arc AB is equal to the measure of angle C, which is the measure of angle ACB. That's what I wanted to prove, that angle ACB is half of arc AB. This angle, the two green arced angles add to the angle 1. So this one green arc angle has to be half of angle 1, which means that angle ACB is half of arc AB. Does that make sense to you? All right, we're on the next diagram. I'll make this slightly smaller so I have more room. On the next diagram, we'll see somewhat the same thing happening. Using what we learned from this diagram, still by theorem 312, but using substitution, I can say that angle AC, and we'll call this point D, we'll use it, angle ACD is half of angle 1, right? Measure of angle ACD is 1/2 measure of angle 1. Tell me why. I'm using everything that we talked about as we came down here. Why is that? Because angle 1 is the exterior angle of that triangle, which means it's equal to the sum of these two interior angles, and they're equal, so each of them has to be half of angle 1. Okay. Now, same idea, angle 2 then, and angle BCD, right? So, measure of angle BCD is 1/2 the measure of angle 2. Everyone's agreeing and understanding what's happening here. Okay. Now when I add these two angles together, BCD plus ACD gives me the measure of angle ACB. So when I add measure of angle ACD plus measure of angle BCD, I'm going to get the measure of angle ACB. And I know that when I add, I can get 1/2 measure of angle 1 plus 1/2 measure of angle 2, which is 1/2 the sum. Okay, now, measure of angle 1 plus measure of angle 2 is angle AOB. This is point O there. So, I know measure of angle ACB is 1/2 the measure of angle AOB. And measure of angle AOB, that central angle, is the measure of arc AB. That's how we get the measure of arc AB. So I can finish out this piece of the proof. Measure of angle ACB is 1/2 the measure of arc AB. We've done 2 of them now. Making this one a little smaller so we have room for the 3rd one. Now, on this 3rd one, you can see marked in green the angle AOD. And you know from what we've done here, excuse me, that angle ACD is 1/2 of that angle. Measure of, and I could say by theorem 312 again, but it's also kind of substitution from what we've already done. It's what we understand about this now. So by theorem 312, and a few substitutions, we end up with measure of angle ACD is 1/2 the measure of angle AOD. And I have ACD in blue and AOD in green, and you can kind of maybe with your mind visualize the exterior angle of the triangle and why that is the case. Just I want you to put the calculator away. Okay. Same idea. Measure of angle BCD is going to be 1/2 of measure of angle, I'll call it BOD. And you can see that I have BCD in red, and BOD has a number 2 in it in red. Okay. If I subtract these angles now, if I take ACD minus BCD, what I get is the measure of angle ACB. Think the blue angle minus the red. Blue angle here minus the red. Blue double marked angle minus the red triple marked angle is what I should be saying. Okay? Gives you angle ACB. And if I take ACD minus BCD in the equations, I get 1/2 of AOD minus BOD. Squished into a really small spot. And now look at AOD minus BOD. That's the green single arced angle minus the red 2 angle. And you can see that that's angle AOB, measure of angle AOB. So this will equal 1/2 the measure of angle AOB. Since that is the central angle that gives us arc AB, that is the measure of arc AB. So again, I have measure of angle ACB is 1/2 the measure of the arc it intercepts. Okay. We can see how all of these happen for the same reason. It's because we're working with exterior angle of a triangle. The inscribed angle, which is marked as 2 red chords in each of these circles, will be 1/2 of the intercepted arc. Right? Okay. We have some corollaries to this theorem. We have 3 corollaries to this theorem. Corollary 1. Corollary 1 says if 2 inscribed angles intercept the same arc, then the angles are congruent. just so you know. I might accidentally. Okay. So what we have is two inscribed angles that intercept the same arc. So I could have angle APB and angle AQB. From Theorem 9.7, what do I know about the measure of angle APB? What do I know about the measure of angle APB from Theorem 9.7? Measure? Yes, it's 1/2 the measure of arc AB. No. What do I know about the measure of angle AQB? It's also 1/2 the arc because it's an inscribed angle that intercepts that same arc. So what must be true about these two angles? If they're equal to the same, they have to be congruent, yes. Both of these are by Theorem 9.7. Now corollary 2. Corollary 2. An angle inscribed in a semicircle is a right angle. Theorem 9.7. Okay. So if we have a semicircle, that means we have a diameter. A semicircle is half a circle, and it's formed when you have two diameters. Okay? When you have a diameter, you have two semicircles. So, if I put, here's my center O, if I put an angle inscribed in a semicircle, tell me what is the measure of a semicircle? 180. This is 180 degrees. And that is an inscribed angle that intercepts the arc that is 180. So since a semicircle is 180 degrees, then, I know, the measure of this angle has to be half of that. So an angle inscribed in a semicircle will be a right angle. This means that I can have any angle inscribed in a semicircle and it will be a 90-degree angle. Corollary 3. Corollary 3 says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Now, the reason for this is when you inscribe a quadrilateral, each of its angles are going to be inscribed in the circle. And you'll notice, if we're talking about angles X and Y here, okay, what you'll notice is that angle X is the inscribed angle that intercepts this arc right here. What about angle Y? What arc does it intercept? The opposite one. Angle Y starts here and ends here just like X did, but it's intercepting that opposite arc. If I call this blue arc M degrees, and I'll put it blue because I'm working with blue, M degrees, and if I call the green arc N degrees, and I changed markers, but of course it didn't change colors because I still had not put one down. Okay, so let's try again. N degrees. What do I know about M plus N? They equal 360 because it's a full circle. So I know that M degrees plus N degrees equals 360 degrees. And I know that X is half of M. X is 1/2 of M. And I know that Y is half of N. Y is 1/2 of N. What will happen if I add 1/2 of M plus 1/2 of N? I get 1/2 of 360, right? If I multiply everything by a half, I end up with 1/2 M plus 1/2 N is 1/2 of 360. So, X plus Y is going to be 180. Okay, we have one more theorem. Theorem 9.8. The measure of an angle formed by a chord and a tangent is equal to half the measure of the intercepted arc. Now, what we have here is, again, three cases because of where the center can lie. Our first case, which is the easiest case, is if the chord is a diameter. Then the angle formed by a chord and a tangent will have to have what measure? Yeah. Which is half of the 180, isn't it? If this is a semicircle, because that's a diameter, 180 degrees, then this has to be 90, which is half of 180. So that's the simplest case. All right. Now, slightly harder, we have an angle that is obtuse here, formed by a chord and a tangent. And you can see that if you would draw that diameter, you have a 90, which is half of this 180. And you have an angle 1, which is half of arc AB, because it's an inscribed angle. And again, you're going to be able to see that if you add half of both of these arcs, you end up with the angle ADP. The other one, which is the hardest of the proofs, is when you have an angle that is acute. So here is your diameter. Here is your tangent. And we're working with this angle. I'm trying to move it to the right spot here. Okay. And we know that we're working with angle 1 here, which is half of arc AB, or let me try again. We're working with angle 2 here, which is half of arc DA, and we're working with a 90-degree angle, which is half of 180. This whole thing is 180, as is this. And then to show that angle 1 is half of that remaining arc. We'll finish this proof tomorrow, but we will have these three cases, and you can probably kind of see why in each case the angle formed by the chord and the tangent is half of the intercepted arc.